that's actually a really good segue into what I'm talking about today, which is the factors that control endowment in greenstone belts. And this is a talk I've given before, but I'm really trying to frame it in a different view here, because after several months of brainwashing at the University of Ottawa with the Metal-Oceans group, I now have a bit of a different perspective on how we view Archean settings. And the real key here is that we're going from settings in the Archean where we're never sure about geodynamics and trying to compare with settings where we're pretty much always sure about what the geodynamic controls are. And so we're looking for features that we can compare and then take that back to metallogeny. I put this slide in basically every single talk that I give, but it's a really excellent first order comparison. This is the Wabigoon. Over here on the left, we've got the Western Wabigoon and Eastern Wabigoon. This is our kind of type example of a lesser endowed greenstone belt. It's not a not endowed greenstone belt. There's really almost no non-endowed greenstone belts on Earth, but it's less endowed, especially with respect to the Abitibi. And as Mark alluded to, the Abitibi really stands out actually at a global scale of being the exception, not the rule. It's the oddball out when we talk about greenstone belts. These numbers here are VMS endowment, calculated in 2005 by Jim Franklin, just divided by surface area of volcanic material within each belt. Okay, so it's a really crude way of doing this, but it does give you a number. The number is sort of meaningless, but the differences between the areas is where we can derive some meaning. So we see here we've got an order of magnitude difference in just dollar value of greenstone material. All right, and that relates to something, and the something could be geodynamics, and what we're trying to understand is how does this relate to modern settings. And so normally when I would give talks like this and talk about the differences between sub-provinces, I'm focused on the key geological features that we can pull apart, because I'm really a field geologist, and I haven't done a lot of the more modern stuff. But now that I'm working on the modern stuff, what I realize is we can make some comparisons, but we have some critical pitfalls when we're trying to compare between areas. One of the key differences, obviously, is a problem that all volcanologists struggle with, and that's that volcanic landforms are very difficult to decipher from stratigraphy because they're really non-unique. Volcanic products and rocks are non-unique to their volcanic landforms, and so it can be really challenging to pick out something like a stratovolcano in the ancient volcanic rock record. Okay, so what I'm going to try to do in this talk is use some different features that we can actually quantify in modern settings really well, and try to look at greenstone belts in that context. And so we're going to look at rifting. Rifting is obviously critical. We just saw these really control VMS deposits. This is the critical factor for VMS, certainly at least from a location standpoint. And it's because it controls your heat and fluid flow dynamics. It's really the critical structures that you're looking at. Basement is something that's really important when we look at modern geodynamic settings, because it influences the rift dynamics, the cross-stratal, the transcrustal connectivity through the crust. Volcanism is something that's really important because it can control fluid flow and it can control fluid types. You can have magmatic volatiles coming in that are derived. But we have to look at volcanism a bit differently, because we can't look at volcanic landforms like we do on the seafloor in the Archean. So we can look at things like water depth and potential water depth constraints. We can look at general volcanic products, but it's really challenging to try to make a one-to-one comparison because the volcanic features are so nondescript. And the last point here is mineral systems. Mineral systems are actually one of the better points to compare between ancient and modern settings. And VMS are probably the best of all of these, except maybe orogenic gold, which have not changed much through time. VMS change a bit through time, but the difference in VMS through time is dwarfed by the difference between just different types of VMS. And when we classify VMS in the ancient rock record, there are many methods to do this, but probably the most popular is just using the host stratigraphy, the host stratigraphic package, which tells us a lot about the geodynamic setting. So let's jump in with the Abitibi. I'm not going to break it down too much, but there are two key takeaway points for the Abitibi before we actually look at some of these features. The first is that it is anomalously well endowed. Okay, it's not just a well endowed belt, it's anomalously well endowed globally in the Archean. It's anomalous in size as well. Okay, it's much larger than the other greenstone belts. There's a lot more volcanic material present here. So it's just fundamentally different in many respects. We've had a couple talks now working through the evidence for rifting, so I'm actually not going to spend a ton of time on that. This is something that we're really focused on because it's really the critical thing we need to compare. But when we do this gravity inversion modeling that you've seen now a couple times, what we see are these long, relatively linear, sometimes sort of anastomosing anomalies in the Moho topography. And as you're going to see when we compare this with the Wabigoon, this is not what we see in the Wabigoon, and I would be willing to bet a fair amount of money that this is not what you're going to see in most greenstone belts. This is probably not what most greenstone belts are going to look like from this mantle topography modeling. And what we see are numerous well-developed anomalies, and they're relatively connected. But it's important to realize that they wouldn't all necessarily be active at the same time, all right? So you're looking at a full-time window. That's another issue with comparing with modern settings where you're looking at one snapshot in time, okay? And geophysically, and to some extent geochemically, these are relatively deep, mature, if you will, rifts, okay? Certainly they're deep anomalies with respect to what we see in the Wabigoon. We can look at the basement of these greenstone belts, and this is something that I really focused on in my PhD and that I think is absolutely critical. And in the Abitibi, broadly, there's very little evidence for older basement, okay? There's a few sparse examples of some older rocks in the Chibougamau area and in the Swayze area, but for the most part, we don't see things like Mesoarchean basement underneath the Abitibi. And where we do see what we think might be basement material in the Abitibi, it's mostly TTG and greenstone material, but this is obviously very difficult to actually quantify. These measurements here are mid-crustal thickness measured from the seismic sections throughout the Abitibi and the Western Superior. And what they show is really in agreement with what we just saw in that mantle topography modeling, that there is a lot of variability between the transects in the Abitibi, because some of these are coming through where these potential rifts might be, and some are not. And others are lying on boundaries like Larder Lake, where we may have had deformation having a significant effect on the overall crustal thickness. What about just volcanology and volcanic products? Again, it's challenging to use volcanic stratigraphy to work out volcanic landforms, but we can look at some aspects of the overall volcanology to tell us about the setting. So volcanism in the Abitibi is really quite varied, but broadly, if you had to put it in one little bullet point, which I had to here, it's mostly bimodal volcanism, all right? There's komatiites in there, there's some odd andesite-looking things in there, there are some rare rocks that don't conform to this, but overall, broadly, we're dominated volumetrically by bimodal volcanism. And critically, there are F3 felsic volcanic units, so these are tholeiitic rhyolites, okay? And these are generated from shallow melting, okay, and they have relatively flat rare earth element profiles as a result. These are common throughout the Abitibi, and critically they occur at multiple periods of time and multiple stratigraphic levels. And what this tells you is that throughout the Abitibi, you are generating melts at shallow levels in the crust, all right? This is, in my opinion, one of the most critical aspects if you want to make a big VMS province, is to have high-level heat flow systems that occur throughout time and not just, say, in one or two spots. We also have lobe hyaloclastite rhyolites, so you don't even need to do any chemistry. You can go into these belts and just look at the rocks, and some things stand out. Lobe hyaloclastite morphology rhyolites, and you can see an example here from Ben Nevis, are rhyolites that have had volatiles held in the lava as it's emplacing, and as a result, they emplace much more almost like a pillow flow, and they have these kind of lobate textures with brecciated margins and hyaloclastite rims all around the edges of it, okay? These are characteristics of relatively deeper water settings because you need water pressure to hold volatiles in the melt while it emplaces. All right, mineral systems, though, are one of the critical points of comparison here. And of course, it's something we really want to understand because that's kind of the fundamental goal at the end of the day for Metal Earth as a whole. When we look at the Abitibi, and I'm specifically here talking about synvolcanic mineral systems because we're dealing with a synvolcanic geodynamic comparison, is dominated by VMS. Certainly numerically, it's dominated by VMS. There are tons of VMS in the Abitibi of all different ages, okay? So this is favorable throughout time for VMS development as well as in certain locations. There are some quote-unquote hybrid VMS, in other words, VMS that have atypical characteristics like, say, acidic alteration or higher sulfidation state sulfides. Some of these can be very significant. Bousquet really stands out. But they're numerically quite rare. Most of the VMS in the Abitibi are chlorite-sericite alteration, zinc, and copper rich. And then we have some interesting epithermal-like systems in the Chibougamau area. Those are very cool, but they're probably not economically all that important. And then there are rare porphyry-like systems, and these can be important, with Cotier being the obvious one in the Swayze greenstone belt down here. It's not showing up on my map, but Swayze's down here, which is a world-class gold deposit, so a fairly significant deposit. But overall, we're dominated by hydrothermal systems with a nice variability in types of VMS. Bimodal mafic, bimodal felsic being the two dominant types, but then also this population of interesting hybrid-like deposits. All right, now Mark already alluded to this, but we're looking at areas to compare, and we're often comparing based on structure and geochemistry. But what we've seen looking at the back arc settings is that geochemistry is largely non-unique. You get morbs, you get calc-alkaline andesites, you get alkaline rocks, back arc basalts, you get them all in a back arc. And so it's really challenging to just use that and say we've got a back arc or anything like that. But what we can look at is the overall setting in the metallogeny. And here the west central Manas back arc is probably one of the best examples from a metallogenic standpoint to compare with the Abitibi. All right, Mark went through this, so I'm not going to spend too much time on the area, but we've got an active subduction zone here running along. This is Papua New Guinea here, running along in towards Papua New Guinea. This is the Melanesian Trench, which is an extinct subduction zone, so subduction has switched in polarity across here, and we had back arc extension, we have back arc extension rather, forming in the Bismarck Sea here. We can look at rifting because it's quite easy to see if you look at a modern seafloor, and we have, again, a relatively high connectivity network of rifts bounded by transpressional or translational rather structures, okay? Again, they're relatively mature, but their geochemical character actually does change throughout the entire Manas Basin. The basement is overall relict arc crust, depending on exactly where you are in this setting, and it's relatively moderately thin. There isn't a lot of good seismic data in this area yet, so we're still not entirely sure about thickness, but that's coming in a map soon to come on Wednesday, apparently, according to Mark. And if we look at water depths, and I'm specifically talking here about volcanism that's related to SMS activity, we've got medial water depths overall, 1,500 meters being kind of the average, but it shallows as we move towards the east. And interestingly, the style of volcanism changes, and so does the style of SMS throughout this area. As we move to the east here, we are getting closer to the subduction zone itself, to the actual active part of the arc, and we have a change in style of melts. So we have almost morb-like melts over in the further west, and then the further east we have increasing subduction zone influence in the melts. But overall, the sequence is broadly bimodal if you were to consider it as a whole, like we did with the Abitibi. Mineralization, though, is what stands out in this area. And I'd also point out that this is one of the best endowed areas of crust anywhere on Earth. So it's a good comparison point just from an endowment standpoint as well. When we look at the Manas Basin, we've got different types of SMS, and they kind of mirror what we see in the Abitibi. In the western portion, we've got mafic rift-hosted SMS deposits that are sort of reminiscent of what you see in the Noranda Cauldron. As we move towards the east, now we have felsic-hosted SMS deposits, and these are somewhat reminiscent of things like what we see in the Powell Block. And over in the further east here, we have systems like Susu Knolls, which are somewhat reminiscent of what we see in these hybrid VMS, in other words, VMS with magmatic volatile input. But also critical is there's synvolcanic porphyry epithermal systems that are forming right now, and alkalic gold systems that are forming, as we just saw, including 60 million ounces on the island of Lahir. So this is a really significant area and has a large diversity in metallogeny, which overall broadly compares to the diversity in types that we see in the Abitibi. So let's move on to the Wabigoon, the lesser loved child, but I would say the more typical greenstone belt globally. This is what most greenstone belts globally look like. The Wabigoon, for reference, here's the Superior Province here. We were just looking at the Abitibi. Now we're looking at this area here, which includes actually the Western Wabigoon and the Eastern Wabigoon right here, with the Winnipeg River and Marmion in between, and these are Gneissic-dominated, Gneissic and Plutonic-dominated areas in between the two greenstone belts. This is the hot-off-the-press model from Chris of the Moho topography. The scale is the same, so the colors are the same as what we saw. And the first thing that stands out is we don't have any blue material here. I'm a field geologist, so everything is just colors for me on maps. But the first thing you notice is there's no blue. There's no really thinned crust here, okay? But we do have a lot of red. We've got a lot of this relatively thick crust. And there are several domains that you can just broadly draw in right away. The first thing that stands out is the Mid-Continent Rift, the northern arm here, where Lake Nipigon is. I've shown the Lake Nipigon intrusions here on this, and you can really see it stands out beautifully. Then you see this core of material here, which is generally thicker and relatively homogeneous crust. All right, this coincides really nicely with where we have fairly good evidence for isotopic Mesoarchean basement contamination, and in places Mesoarchean rocks on surface. So this looks like you've got a core of older basement material. And then in the Western Wabigoon over here, we're starting to develop some of these anomalies that are somewhat reminiscent of the Abitibi, but they're at a way different scale. They're much, much smaller anomalies in terms of the change in thickness of the crust. Okay, so that you do not see a huge variability in crustal thickness throughout the Wabigoon. We can see this as well in the seismic, but I'll point out that a lot of these seismic transects, these are box and whisker plots, a lot of these seismic transects have lots of variability within the transect, in part because many of them cross the Quetico Fault and are going into other sub-provinces. So it's not the easiest thing to compare with the variability in the Abitibi, but overall, the whole sequence just displays thicker mid-crustal material in the Wabigoon. And this really agrees with the basement, because we've got evidence, isotopic evidence, for lots of older basement material that we don't see in the Abitibi. We can look just in the field as well. We can go into the field and see some key differences. We see in the Wabigoon lots of shallow water and subaerial volcanic units. And they pop up at various locations in various periods in time. All right, and this is an example from the Eastern Wabigoon from my PhD area. It's a beautifully flow-banded dacite. Flow banding is coming up and down here in your screen. And you can see it's terminating at 90 degrees to the flow-top breccia. Here's the flow-top breccia here. It lacks any hyaloclastite. And so we're looking at a rhyolite here that may be subaerial. And certainly this is what we would expect. We would expect some hyaloclastite in there if that was deposited subaqueously, and we don't expect this angular relationship. There's also large andesite centers in the Wabigoon, including the largest one anywhere in the Archean. This really stands out. There are andesites in the Abitibi, but they're not volumetrically really that important, and they're geochemically a bit different. They're really just fractionated basalts. They're not a mixing andesite like we would see and like we see here. And we don't really have any Neo-Archean F3 tholeiitic rhyolites. There are only a few in the entirety of the Wabigoon, and in fact, areas like the Eastern Wabigoon have none. F1 is now the dominant signature of rhyolites, so deep melt source rhyolites that have formed in a setting where you haven't rifted and thinned the crust. And we just saw geophysically that agrees with the geophysics. Now, what about the mineralization? We'd expect this to be quite different, and in fact it is. We're not now dominated by typical VMS. There are still some VMS, but they generally have atypical characteristics like acidic alteration assemblages that have been metamorphosed. We have things like these polymetallic vein deposits. We have potentially true epithermal-like deposits like the vent, which is shown in the top right here, which are gold-rich pyrite stringers in kyanite quartz material. This is a dacite that's been altered to entirely kyanite and quartz. In other words, all of the major elements have been leached out except for silica and alumina. And there are also porphyry-like systems here. But the critical thing is that these are all small. So there's a low overall endowment. Even the economic VMS in this area are small. So the endowment overall is quite low. But we now have this dominance of magmatic hydrothermal systems. So is there an example for this? Yes. In fact, there's quite a few. But probably one of the best from a metallogenic standpoint is the southern portion of the Kermadec Arc. Cornell-Durand wouldn't like me saying this, but it's also a lesser endowed area in the crust. Okay, there's not a lot of big SMS deposits here. The Kermadec Arc extends north of New Zealand up towards, we just saw maps of the Lau, which is up here. It's essentially, this is the Kermadec-Tonga Arc chain here that runs up here, and the Lau is the back arc in the north. Here we've got the Kermadec Ridge running down here, so this is the active arc. The Javier Trough here is initial back arc spreading. And right away, you can just see there's a lot less rifting than what we just saw in the Manus Basin, right? We now have one relatively linear, relatively poorly developed rift. Again, it's geochemically quite immature in that you pull out a lot of andesites when you sample this, so it's not what we are seeing in the greenstone belts. And here we've got an interesting basement situation. Mostly we're dealing with relic arc crust, but in the south here, we are coming into the Australian continental margin in the topovolcanic zone. And this is where things start to get really interesting. I'll come back to that in a second. First off, the volcanism throughout here is all subaqueous to subaerial, but relatively shallow water, okay, sometimes emergent, such as at the White Island in the topovolcanic zone, and it's fractionated andesite suites, andesite cones, basically, a whole series of them with SMS. This is a PERSCOM from Cornell-Durand who swears on his life that there's 80% of the SMS vents in the Kermadec Arc have some evidence for magmatic volatile input, if that's magmatic helium, magmatic gas directly coming out of the vent itself, or acidic alteration associated with it. And then, of course, we have famous epithermal systems like the one at White Island, which is in nearly every epithermal review paper as the type example of a modern forming epithermal system. And so in conclusion, there are significant differences in the geodynamic features between the greenstone belts, and they vary quite nicely between the well and less endowed belts. The styles of mineralization reflect these changes, and we see similar patterns on the modern seafloor. And this is a diagram from Houston et al. In 2010, and if you just remove the subduction zone from your mind, you don't need to even have it in this diagram. The rest of the diagram actually works really nicely with what we're seeing. Rifted, thinned crust with very little basement generates your relatively typical VMS. Thickened, partially rifted crust with some basement generates your magmatic hydrothermal systems in these atypical sort of hybrid VMS. So the key aspects are rifting, basement, and magma series. There's many more, but those are the key ones we had time to talk about today. And just lastly, we can pull some exploration tools out of this. There are things we can start to use even right now, right away. Volcanology as a broad scale, just evaluating whether or not we've got low pyroclastite rhyolites, which are important for showing you've got deep water volcanism. The F-type rhyolite classification is still one of the best ways to evaluate regional prospectivity for VMS because it tells you how deep your melts were in a broad area. We're now generating with Metal Earth large isotopic data sets, particularly for the northern superior, which are going to be really interesting, I think, from a VMS exploration point of view going forwards. An older basement seems to be a bad thing, so perhaps areas like the Uchi will be interesting with that respect. And lastly, this MOHO topographic modeling, which Chris has explained to me about 5 times, but I still don't really understand. But the MOHO topographic modeling is really powerful. It shows you where all the where all the VMS deposits are in the Abitibi. Okay, and it shows you them really, really nicely. So I think that's a really powerful tool, and the data, of course, is free. You just have to hire somebody like Chris who knows how to do it. And that's it for me. Thanks.